Okay, fine. Yes, guys. So what were we discussing in the last class? Is my voice clear now?
Yes, sir.
So what were we discussing in the last class? What are the different topics that we have touched on? Guys, that class will be really interesting if you guys get involved in the class and start to speak and start to interact with me. Every time, if I just call your name and intentionally, if I call your name and just instruct you to speak on that, that will not work out every day, is it? So just try to interact. A minimum common questions I would ask. That's it, right? So as long as the session is interacting, it will be more interesting to understand from your side, and it will be more interesting for me to teach more. That's all. Okay. So try to interact more so that if the class goes well, we shall end up within 40 minutes. That's enough for the BTD. Okay.
Last class we have discussed about the path and process, the point function, path functions.
Path and processes. Okay.
Yes, point
And
function,
point function
path
and
function.
path function.
Yes.
Yes. What
We
else?
have gone through some state point and state diagram also.
State point and state diagram also. Okay.
Yes, that's it.
That's it. Any other things which Kartik did not tell about other guys? Any other points that he did not tell? Shehzad?
I mean, that's all I noted too, sir.
Hmm?
Those are the 3 points I noted too.
Okay, fine, fine, fine. So these are the important points that we have discussed, and I even told you in the last class that whatever we discuss in this class would be of very important, right? Okay, fine. So I have just said you what is a point function and a path function. So point function is something where if there is a process, something like this, okay, all this is a thermodynamic process. All these are the state points here. This would be state 1, this would be state 2, this would be state 3, and this would be state 4. So for all this processes, okay, there are different states, state 1, 2, 3, and 4. So since I can plot it on the PV diagram, let us see. So I can define the pressure at state 1 as it, okay. I can define the pressure at state 2, okay, directly. I can just go back because one point on the graph, on the point, a single point on a plot is more than sufficient for me to get the parameter of pressure. So that's why I told you pressure will be called as a path function. And similarly, if I want work done at 1, I cannot define it as work done at 1. I must say work done from 1 to 2 because it is a path function. It depends upon the path of a system like this. It depends upon the path of a system. So that's why I must say W1 to 2. I cannot just say W1 nor W2. Okay, that is totally wrong. So you have to say it as W1 to 2. Since why 1 to 2? Because it is a path function, depends upon the path. In order to specify the path, I'll be using 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So these are the different paths in this particular cycle. So 1 to 2 is being this one, 2 to 3 is being this one, and 3 to 4 is this, and 4 to 1 is this. Okay, that is how you will calculate the work done. Or it comes with the heat flow also. Just a moment. Okay. So that is how you calculate the work done. So work done, I told you, can be specified as W1 to 2 or W2 to 3 or W3 to 4, or it could be W4 to 1 also. Okay, so you can calculate all of the things, but you cannot calculate W at state 2 or W at state 3. You cannot do that. Why? Because this is a W, that is, the work is nothing but your path function. So work is nothing but your path function. So you have to specify it as 1 to 2. You have to completely specify the total process of it. And it goes in the same principles for the calculation of heat also. So the heat is denoted by Q and work is denoted by W. So work in W is denoted as work and heat is denoted as Q. So both of these parameters are the path functions. Even this is a path function as well as the W is a path function. So if I want to calculate curve, I must specify a certain path. Suppose I take a path from 2 to 3. Okay, curve 2 to 3. I cannot say cube 2 because cube 2 indicates cube will be a point function. So it is not a point function, it's a path function that goes from 2 to 3. That's why you have to specify it as cube 2 to 3. Okay. So this is what I have told. Now I will be talking about what is an exact differential and what is an inexact differential. Let us see the points. Okay. Now see, if I want to calculate dP, I mean to say the change in the pressure, I can just calculate P2 minus P1. So I can go for the value of P2 here and go for the value of P1 here. Whatever is the value, I can just subtract them, okay, and get the value of the change in the pressure directly, okay. But but if I want to calculate what is the difference or summations of the work, I cannot do so. That means the integration from 1 to 2 of dP, that means the difference in the pressures at state 1 and state 2, that is here, the state 1 and state 2, can be calculated as P2 minus P1. Okay. Why? Because T, which is your point function, is also an exact differential. It is an exact differential. But the same thing, if I want to calculate the change in the pressure, so change in the pressure, sorry, change in the work, if I want to calculate the change in the work, that is from 1 to 2, I cannot do it as W2 minus W1. Difference in the state's pressure, I cannot do it, which is not equal to W2 minus W1. So that's why it is called as inexact differentials. Okay. The difference between the properties of the two states, if it is calculated by the exact subtraction of those two properties at that particular states, then it is called as the exact differential. Suppose that if you want to calculate the difference between the two properties at two different states, but if you cannot calculate just by differencing in the sense subtracting those two parameters at those two states, then it is called as inexact differentials. So remember this particular thing, which is very important. Is the exact differentials are always indicated by D. Okay, they will use the suffix D. And the inexact differentials are always calculated or indicated by word delta, by the letter delta. Okay, this is how it goes. So to summarize all the things, the pressure, volume, and temperature are the point functions. And remember, all the point functions are exact differentials. Why they are exact differentials? differential because they can be calculated as the difference between the two parameters at two different states. Okay, there are exact differentials, and for that difference, we can indicate with t. Okay, and coming to the second point, the W and Kev are the work and the heat, okay, which are path functions, okay, which are path functions, and all the path functions are inexact differentials. To indicate the difference between inexact differential parameters, we use the letter delta. So this is the overall summary of the point, path, exact and inexact differentials. Okay. Any doubts as of now? Any doubts? Benoy? Benoy? Are you there, man?
Yes, sir. Yes, sir.
So concepts are clear with the point and path functions. So why point function is called an exact differential?
I don't know.
So were you listening the class, Benoy?
Sorry.
Were you listening the class?
Yes, I was listening to class.
Then okay, no problem. You just go through the notes. If you have any doubts, you can contact me, and make sure you say me what is exact differential and inexact differential in the next few minutes. Okay, go
Okay.
ahead. Chandan,
Sir, I didn't get, sir.
you didn't get in the sense
I was not listening, sir.
why?
I joined now, sir. There was problem with my phone. I joined from laptop.
Acha, fine, no problem. Gaurav,
Yes, sir.
yes, Gaurav. So what do you mean by exact and inexact differentials? Why the point function is called as exact differential?
The path function is between two work from one place to another, and a point is on exact position. So the difference will be correct. The different work
Okay,
function will not equal.
okay. Niharika,
Yes, sir.
so why the point function is called an exact differential?
Sir, the difference between the properties
Mm-hmm.
between state 1 and state 2 are always the same,
Mm-hmm.
irrespective of the path which they follow.
That's great. So I have a
So,
note talked about the path, is it? As of now.
uh,
So just remember, guys. Yeah, Niharika. Just remember this. The point functions are called the exact differential just for the reason that they can be calculated as a difference between these two states. Okay, if I want dp from this process 1 to 2, I can just write it as p2 minus p1. So dp would be equal to p2 minus p1 straight away. Okay, you can calculate just by subtracting those two parameters at two different states. But when it comes to a path function, you cannot do so. So that's why delta W is not equal to W2 minus W1, something like that. It is not equal to the difference between the two parameters. That's why it is called as an exact differential. It is so simple. Okay. Amit Sangoli. Amit. Amit. Okay, it's not that. Rajat Rai. Rajat?
Sir.
Yes,
Hello.
Rajat. So,
Yes,
got the
sir.
meaning of exact and inexact differentials?
Uh, yes, sir. Kind of.
Kind of. So, what did you understand?
So that difference in path, something difference in the path, sir. Like D1 minus D2 minus D1, sir.
Okay, okay. Shravan Pujari. Shravan. Shravan. Okay, he doesn't think so. Next, Pratish Suvarna.
Yes, sir.
Pratish.
Yes.
Yes, Pratish. Got the meaning of exact and
Yeah,
inexact
yes, sir.
differential?
Yeah.
What is that?
The change can be written as difference between their states in exact differential.
Exactly. Exactly. Super. And what about inexact differentials?
We can't write in like we can't write the difference
Difference between the two states.
between them.
Yes. Two states. The change cannot be calculated as the difference between the two states. Is it? That's great.
Yes.
So, which functions are pronounced to be an exact differentials? Whether the point functions or path functions.
Point functions.
Point functions are exact differentials. Which
Yes.
are inexact differential? Which functions are inexact differentials?
Path functions.
Path functions are inexact differentials. That's great. Shehzad.
Yes, sir.
So, work is an exact differential or inexact differential?
It is an inexact difference.
It is an inexact differential. Why it is an inexact differential in the sense? Because it is a path
Path
function. Okay, that's great. Sumant.
Yes, sir.
So, volume is an exact or inexact differential?
It is an exact.
It is an exact differential. Why it is
Yes.
called as exact differential?
Because it doesn't change. Yeah.
Because
It is an inexact. It changes.
it is an inexact. Why it is an inexact?
It changes during time.
Okay, so were you listening, man? Seriously?
No, sir. I joined little late due to network problem.
Okay, 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 fine. Ramdas.
Yes, sir.
Yes, Ramdas. So
Sir,
I ask
volume
uh,
is an exact differential, sir, because the value of the volume can be found out at any time. It's a point function.
it's a point function, and if I want the change in the volume, I can just say it as V2 minus V1.
Yes,
I
sir.
will get the value. That's
Yeah.
why it is called an exact
Point function.
differential. Great, guys.
Exact.
That's it.
Yeah.
Great. Exact differential or the point function, both mean the same. Okay. Hope you got the things right for the path and point I have explained you. Exact differentials can be calculated as the difference between the two properties at two different states, whereas the path functions, which are inexact in nature, cannot be calculated as the difference between the two states. So D is always used to denote the exact differentials, and the delta is always used to denote the inexact differentials. Okay. Now, next point, which I try explaining you now, is very important, and it is with respect to the process. So whatever process I'll be explaining you, all the five processes now, those will come for module 1, module 2, module 3, and some parts of module 4. So it is very important to understand it at the start of the thermodynamics. Okay, so just concentrate, guys. So any plot on a PV diagram like this, any plot on a PV diagram, if any process, I mean to say, it might be isobaric. I told you there are five processes. Can you name those five? Can you name those five?
Isobaric,
What are the five
isochloric,
different?
isothermal, adiabatic,
Isobaric,
Adiabatic.
adiabatic, and one more?
isochloric,
Isochoric.
Isochoric.
Polytropic
Next, isothermal.
and polytropic.
Okay. Adiabatic and polytropic. Okay, except the ideal process. So all of the processes will come in these five categories itself. There are no the other processes which come. Okay, so in order to plot these processes on a PV diagram like this, okay, if I want to plot these processes on a PV diagram, all the plots follow this particular equation, okay, which says PV to the power of K is equals to constant. Okay, so P is nothing but your coordinate axis to the power of K is equals to constant. So by using this master equation, I can plot each and every process on a PV diagram. I mean to say, I can represent each and every processes in a PV diagram. Okay, how we shall see now. Okay, there is a call. Just a minute. Yes, guys, sorry for that. I was talking about all of these five processes. There might be your isobaric, isochoric, isothermal, adiabatic, and polytropic can be represented somehow in a PV diagram by using uh, the relationship PV to the power of K is equals to constant, how I'll be discussing now. Okay. Now, if I put the value of K to be 0, if I put the value of K to be 0, what happens, guys? So PV to the power of 0 is equals to constant. Anything to the power of 0 is what?
1.
Exactly. So anything to the power of 0 is 1. So P is equals to constant. So that means which process, which is that process where the pressure is constant?
isobaric,
That's great. So for isobaric process, the pressure is constant. That's why the value of k is equals to 0. Okay, then it looks on the PV diagram as such. Okay, okay. So the first process is being isobaric process. Okay, it looks on the PV diagram as the horizontal line. Okay, where the value of k is equal to 0. The second process, isochoric process. So for an isochoric process, which is constant? For isobaric process, the pressure is constant. And for the isochoric process, which one is constant, guys?
Volume.
So volume. So volume will be equal to constant. For isochoric process, the value of k would be equal to infinite. If the value of k is equal to infinite, then the volume would be 0 because if you reciprocate it, it will get the value. So isochoric process in the sense the volume has to be constant. That's why it is represented by a vertical line like this. Okay. And the third process, which is isothermal. So in the isothermal process, which one is constant?
Temperature.
Temperature is constant. So the value of k for the isothermal process would be just 1. So if you substitute k is equals to 1, then it would be isothermal process. And the representation of it on a PV diagram is a curved line like this. Okay, so we have to definitely specify the states like the state 1, state 2, and it is going in this way. State 1 and state 2, and it is going in this way. And state 1 and state 2, it is going in this way. So on the PV diagram, the isothermal process is a curved line. Okay. Now, fourth process. So fourth process is adiabatic process. Now, for an adiabatic process, which is called as isentropic process. So adiabatic process is also called as the isentropic process. Why? Because the entropy is constant here. What is entropy? You'll be understanding in somewhere between module 2 ending, where you come across the second law of thermodynamics. You'll understand what is entropy. As of now, just remember, your adiabatic process is nothing but your isentropic process, where the entropy, which is denoted by S, is constant. Okay. Now, the value of K for this particular process is equal to, it is not 1, it is not infinite, or nor it is not the 0. So it will be equal to, when the value of K, if it is equal to the ratio of specific heats, which is denoted by gamma, then it is called as an adiabatic process. So what is the ratio of specific heat? Ratio of specific heat is nothing but the value of Cp by Cv. So gamma for air is around 1.4. Got the point? Gamma for air, that is the ratio of specific heat's value for air. My slope of the curve, if my slope of the curve or the value of k, if it is exactly equal to the ratio of specific heats, if it is exactly equal to the ratio of specific heats, then your process is termed as adiabatic process. Okay, so that is how it is called as. So similarly, your adiabatic process will also look like a curved line in a PV diagram. So it is the initial state, final state 2, and the way it goes is like this. Okay, so this is your adiabatic process. And the last process now. Last process is Which one? The polytropic process. Okay, now, for a polytropic process, nothing is constant. Just remember this. For a polytropic process, nothing is constant. Let us have a recap of all the process now. For isobaric process, the pressure is constant. For isochoric process, the volume is constant. For isothermal process, the temperature is constant. For adiabatic process, entropy is constant. For a polytropic process, nothing is constant. Okay, that is the significance of a polytropic process. Now, what will be the value of K for this then? So K, see, if it K, the value of K, if it is 0, then I will call it as isobaric process. For isochoric process, the value of K is infinite. And for isothermal process, the value of K is 1. And for an adiabatic process, the value of K is exactly equal to the ratio of specific heats, the value of ratio of specific heats. But if the value of K is not 0, not equal to infinite, not 1, but it is also not equal to the ratio of specific heats, but it is something other number which has no significance, I can just call it as n. It might be 1, 2, 3, 4, whatever it is, which has no significance whatsoever, then such a process is known as a polytropic process, where the value of K is not 0, not infinite, not 1, nor the exact value of ratio of specific, something other number, then it is known as the polytropic process. Even the polytropic process is a curved line on a PV diagram. Okay, all these are curved lines. The isothermal process, adiabatic and polytropic, all are the curved lines. Okay, so these are the 5 processes. Let us have a recap again. So isobaric process, the pressure will be constant and the value of K is 0. It is represented as a horizontal line in a PV diagram. Okay. Now, for an isochoric process, volume is constant. The value of K would be equal to infinite. That is why it is represented as a straight line, straight vertical line in a PV diagram. For an isothermal process, temperature is constant. The value of K would be equal to 1 and it is represented as a curve in a PV diagram. For an adiabatic process, the entropy remains constant and the value of K is equal to the exactly equal to the value of ratio of specific heats, then it is represented as a curve in the PV diagram. Then it is called as an adiabatic process. Now, for the last one, polytropic process, nothing is constant here. Everything would be changing. And the value of K is not 0, not infinite, not 1, nor it is equal to the value of specific heats. It is just some arbitrary value. Then such a process is known as a polytropic process. Even the polytropic process also can be represented as a curve in a PV diagram. So this is all the things about all the processes. Any doubts here? Any doubts, guys? Ashwita,
Yes, sir. No doubt.
any doubts?
No, sir.
Okay. Just take these things which I am just showing now, which I have written. Just take in your notes. Okay. Okay, done?
Yes, sir.
Okay. So even the second
Go
hair
for
is...
it.
Okay, man. Even the second hair is mine. So we will be continuing the class. Take a break of 20 minutes and we shall meet again. Don't leave the meeting, just let me go on. And we shall come back at 10:30. That's fine, guys. 10:30 is fine, correct?
Yes, sir.
Okay.
Okay, man. Have a break and then come back.